was trying to find some stuff on Ernest Rutherford before. This is a simple reaction when he was hitting alpha particles into a nitrogen atom, and I couldn't even find it on the internet. So, we're going to learn how, after helium, 2 heliums would be beryllium-8. There's nothing in beryllium-8's box here, is there? What happens is a triple alpha process, they call it. Hans Bethe discovered this. He came to this conclusion on a train ride, I guess is the famous historical aspect of that. 3 alpha particles. 2 come together, a beryllium-8, you'll see it with a little asterisk, high energy. We're talking microseconds, I know, nanoseconds, I'm not even sure, but so fast that as soon as those 2 come together, if another alpha hits it, it'll go over an energy barrier to the point where carbon-12 is now a stable molecule. Stable nucleus, 6 protons, 6 neutrons. Carbon-12, carbon, most life-essential element, most people call it. Anything organic chemistry, is going to have carbon as its main atom. So, carbon is made in stars. I'll tell you a story. This is why I got into physics anyway. After I got my degree in chemistry, I thought, organic chemistry. I studied for 2 years, another year of biochemistry. I didn't know where carbon came from. Where does it come from? Our sun is fusing protons to make helium. Not enough energy to fuse 3 heliums to make a carbon. What you need to do that is a star at 100 million degrees. Jupiter, the orbit of Jupiter, there's a star whose atmosphere goes that far out. It's called Betelgeuse. Astronomers will tell you, oh, it's a red star, it's cool. Well, in the core, since that star is so humongous, all you see is the red light on the outside coming. It's hot on the inside. So a triple alpha process is nothing, 100 million degrees. So in order to fuse carbon, you need higher energy, hotter temperatures. Our sun is still right now fusing the protons to heliums that some other star had done earlier. Because as I tell you, our bodies, we are older than the sun. And I'll say God. God made us way before the sun started even spitting light out, okay? Well, I don't know about that, but the elements he made, okay? The elements, carbon, again, was made in a star that our sun isn't hot enough to make. Hey, maybe our star once did, and now it's just shrinking in. Maybe things work backwards. You never know. Or do you? People tell you they know. So maybe our star once was bigger and made elements like iron, and then got smaller in carbon. Now it's just making helium for light. But anyway, the process of what they call binding energy above iron, and I'll call it iron, cobalt, nickel. If you look on the periodic table, these are called noble metals. Right here in that big gap there, you're going to see iron, Fe, Latin for ferrous, cobalt, nickel. These elements are fusing inside the cores of stars. So that's how elements are made. Now, when we go back to the table of the elements and then look at the chart of the nuclides, they call these are all isotopes, I started noticing some trends, okay? Nobody teaches a class on this. I took nuclear engineering, and that is where they even introduced this chart of the nuclides. And luckily, I had a very excellent teacher, professor. I call them professors when I have utmost respect for them and the way they teach. Professor Dunlap, I guess. I think his dad worked on something, that stuff in the 40s. So he loved physics. I started my lectures like his. Today, for your enjoyment, he'd always come and say that. But carbon-12, okay? Carbon with another alpha particle now. The first building blocks were the protons. So you learn the protons are making neutrons. They go to make helium. Now the next building block, which essentially, I won't say it. Building blocks of alpha are like nails in a building. There's going to be a ton of them, okay? hydrogens would be the nails. Let's see, the heliums would be like the 2x4s, okay? The studs, the helium studs. So carbon with an alpha particle, oxygen 16. This is another life essential element. Stars are fusing alpha particle, the heliums together. Another helium hits oxygen 16, neon 20. So what we see when we look at the abundances of elements that are in the universe, in our solar system, for example, we're going to see there's a lot, well, not in ratio percentage to hydrogen or helium, but there is enough carbon that I'll say there's a lot. Carbon, oxygen, lots of oxygen on Earth, right? Neon, not so much. But neon is a noble gas, and that's a chemistry topic that we are discussing nuclear physics at this point. So here, to make the periodic table look more fun, is a table that is called Evolution, Survival of the Stablest. Do you get it? Elements like beryllium-8 that we just saw do not stick together. The elements that are life essential to humans are carbon, nitrogen, oxygen. Isn't it funny how these three are right in a row? We know that carbon and oxygen are made in the stars from the helium alpha particles coming together. And I'll tell you, where does nitrogen come from? I don't know. And I'm curious about it. But as an aside, carbon forms bonds and molecules to make fats, which are carbon and hydrogens. Through photosynthetic processes, carbon and hydrogens get to add an oxygen, and CO2, which is in our atmosphere we've all heard of. CO2 in water can make sugars, which are carbon, oxygen, and hydrogen. And to do that process, you need enzymes that are made from amino acids that involve nitrogen. So your three food groups: fats, consider that just carbons. Sugars, carbon and oxygen. Protein, carbon, nitrogen, oxygen. These three are the most life essential elements. You can't just say that carbon is the most life essential element. It's carbon, nitrogen, oxygen. The chart of the nuclides. After these are made, here's the hand. I need the hand. We'll pull the table down here. You got to picture this happening in stars, okay? The alpha particles, somehow in this process, alpha particles are either emitted or they're building up by alphas. But what I noticed was a trend here. 100% of the isotopes that you find for a sodium atom anywhere in the universe, because of its stability rules, I would have to imagine, 11 protons, 11 neutrons. 11 protons, 12 neutrons. This sticks together. 11 protons, 13 neutrons. Doesn't stick together. Sodium with a mass of 23 is going to have 11 protons, 12 neutrons every single time. You will never, I guarantee, you can search every sodium atom in this universe, and if you find any that are stable with more than 12 neutrons or less than 12 neutrons, I'll pay you $1 million space bucks. Anyway, what I noticed from the chart here, from sodium to aluminum, this is an alpha particle away. Add another alpha particle. Aluminum with 4 mass, 27 to 31, phosphorus. The only isotope that you find of phosphorus, any phosphorus atom, isotope is that one number of neutrons, 16 neutrons. The only one you'll find. Aluminum, same thing. There's one isotope, one nuclide. There's so many different names for the same thing. They're talking about the atom nucleus. The number of protons doesn't even come into play because if you change the number